a quick recap of what we did in the last class. We derived the transfer function theorem with regard to interreciprocal LPTV networks, and the basic idea was the following, or rather I should say the result is the following. Let us say you have a network N, this is LPTV at Fs, and you excite port 1 of the LPTV network, say with a current e to the j 2 pi Ft, and the voltage that you obtain at the output port, for instance, apart from having a whole bunch of other components, it has also a component at F, and if we denote the gain by H sub 0, which is the 0th order harmonic transfer function of the network from input current to output voltage, this is H naught of j 2 pi f e to the j 2 pi f t plus other terms. And what we found yesterday was that if you created the adjoint network, which is also LPTV at Fs, and you excited the output port with e to the j 2 pi f t, the voltage developed at the frequency f across the input port will be H 0 j 2 pi f e to the j 2 pi f t plus other terms. The key point is to observe that these two transfer functions are the same, and there are well known rules for how one can obtain n hat from n, and we saw how we do that. We basically, if you have an element in n, what you need to do is find an element whose MNA stamp is the transpose of that element, and it is just simply, once you know that, it is just simply a matter of element to element replacement in the network. Now, so the key points were that both input and output frequencies are the same. So, the obvious question is, what if the output frequency we are interested in is different from f? All right. So, in other words, what we are interested in therefore is this is the network N. So, if we are interested not in H 0, but say H, let's use M, right, and in which case this will become the output frequency of interest will be f plus m f s times t, right. And the question is, how can we exploit or how can we understand reciprocity in this case, right? And again, to find H sub m, How do we do this? Well, it's pretty much same old, same old. What do? We write the G matrix, right. So, again we use, we assume that this node is 0, this is 1, this is 2 and this is 3. G times the voltage vector. So, that is basically V1, V2, V3 and a whole bunch of other terms equals the current source vector that is going to be exciting the input port, right, and that must be 1, very good. So, this must be 1 capital K plus 1, and remember that 1 capital K plus 1 is defined as a vector with all zeros except the K plus 1th term. Okay. All right. And what will all the other terms, column vectors in this on the right side be? They will all be 0, where each of them is, each 0 is basically a 2k cross 2k plus 1 cross 1 matrix, right. So, as usual, therefore, once you get, so if you solve this set of equations, you will you will be able to get the voltage vector, but that is not the vector that you are actually interested in. You are only interested in V2 minus V3, and even in that you are not interested in all the terms, you are only interested in the what do you call, the strength of the mth tone at F plus MFS, right. So, the output, so at what do you call F plus MFS, which basically is equal to H sub m of j 2 pi f, is simply given by what do we need to do? We need to multiply this by, we are not interested in V1, we are interested in V2, and which term of V2 are we interested in?
F plus MFS is there.
Correct. So,
K plus 1 plus m.
very good. So, you will be interested in the K plus 1 plus mth term. So, this is K plus 1 plus m transpose, all right. And remember what is this 0 here? What kind of vector is 0? The 0 there,
That is the
that is a,
has to be row vector.
it is a row vector of size 1 row and 2k plus 1 columns, and likewise this 1 sub k plus 1 plus m transpose is also a row vector. The next one will be minus 1 capital K plus 1 plus m transpose 0, 0, 0, etc. All right, and this multiplied by V1, V2, V3 will give us our desired transfer function, which is H sub m of j 2 pi f. And as usual, this is a scalar, and therefore does not change if transposed. So, so I can also write this as h of j 2 pi f m. So, if I transpose both sides of this equation, what I will get is, oh by the way, what is this this guy here now? this chap is nothing but
G
let me, this is nothing but G inverse times,
excitation vector.
yeah, let me copy and paste this. So, the voltage vector can be found by just simply computing the solution of that matrix. So, G inverse times the excitation vector, which happens to be 1 capital K plus 1 and so on, right. So, if you transpose it, I can reinterpret this. So, if I transpose both sides of the equation, I can we can see that h sub m of j 2 pi f can also be written as 1 sub k plus 1 transpose 0 0 blah 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 times G transpose inverse times 0. I am not writing the transpose on the zeros because it is understood, right. So, this is going to be 1 k plus 1 plus m, this is minus 1 k plus 1 plus m and 0 0 0 and so on. Okay. Does that make sense? All right. Now, how do you interpret this? You can interpret this equation on the left or the terms on the left in the following way. You can think of this as the, in the original network, this was the excitation, this was the MNA stamp of MNA matrix rather, corresponding to the network N, and this is the measurement. Right. You can now interpret, if you interpret the order of the terms the same way, this is the excitation and G transpose is the MNA matrix of a new network, which from our past experience is simply the adjoint of the original network, and this is the measurement matrix. Right? Okay. Now, how do we interpret in network form what this means? So, basically we have our network, the network, what we call it is n hat, all right, and all right, and where do we add the excitation?
The output.
So, this is node 1, this is node 0, this is node 2 and this is node 3. The excitation is between port 2 and 3 and I mean between nodes 2 and 3, and what is the frequency of excitation?
Plus K MFS.
Yeah, very good. So, basically the excitation is now a current source between nodes 2 and 3, and more importantly the excitation is at a frequency, this is e to the j 2 pi f plus MFS times t, right. So, So, this corresponds to node 2 and this corresponds to node 3 and this corresponds to tone at f plus MFS, correct. And all right. And what comment can you make about the measurement? The measurement is now at port 1 and what component are we interested in measuring
HM like F.
No, what is this saying? This is you are measuring the voltage at node 1
Frequency of F.
and we are interested in measuring, I mean, and the quantity of measurement, the frequency of interest is
F only.
f only, right. So, this is basically saying that this is f. So, what you will get, what the equation is telling us is that if you excite port 2 of the adjoint network, right, with an input at f plus MFS and observe the output at port 1 at the frequency f, what is the ratio of the what will you get? What is the magnitude, what is the strength of the tone you will get at f?
It minus
What is this equation telling us?
it's like frequency is down converting to F plus.
No. What is this equation telling us?
Okay. Output at the F.
The input tone is at f plus MFS. If you apply an input tone between nodes 2 and 3 at the frequency f plus
The
MFS,
component is H of
and you look at the voltage at port 1, right, with whose component is at frequency f, that transfer function is basically
HM of
h sub m of
J2.
j2 pi f, which is plus other terms, right. Okay. And what is Hm of j2 pi f? It is also the transfer function from an input frequency at f to an output frequency at f plus MFS in the original network. You understand? So, this is okay. All right. Let me draw that. So, this is the original network. This is h sub m of j2 pi f times e to the j2 pi f t plus other terms. All right. So, what this is telling us is that I mean, and by the way, what comment can you make about if you apply a tone at f plus MFS and look at the output at f, what, I mean, how will you that is nothing but
Harmonic transfer function.
it is if you look at the network n hat, right, that is the harmonic transfer function from the output port, sorry, h hat of the output port is 1, the input port is 2, right, and what is the index of the harmonic transfer function? Minus
M
minus m of what frequency?
That is like J2 pi f plus m.
J2 pi f plus mfs, right. So, that is because the input frequency is f plus mfs, the output frequency is f plus mfs minus mfs, which is f, and so this is basically h12 hat of minus m of J2 pi f plus mfs, and this must be by interreciprocity, this must be the same as h21 of m of J2 pi f. All right. So, this is telling us that not only are the ports of excitation and where you measure the response, they are interchanged, right, but in the input frequency and the output frequency are also interchanged in the adjoint network, right. So, this is one form of the theorem. Now, if you replace f with, so now with f minus mfs, right, in the above equation, I mean f is an arbitrary frequency. So, I can replace it with anything. So, then that this will become h hat 1 2 minus m of J2 pi f must become h21 m of J2 pi f minus mfs, all right, and then m is also arbitrary. So, I can replace m with minus m, and therefore, you will get another form of, I mean it is basically the same, it is basically interchanging n and n hat, right, h hat 1 2 of m of J2 pi f equals h21 minus m of J2 pi f plus mf. All right. So, this is we will discuss why this is important in a little while, but so I will box the theorem. This is called the frequency reversal theorem. And that is what we are going to see next. So, what I am going to